good morning, good evening, depending where you are. This is the last lecture of the regular part about text representation learning. So representation learning also means feature learning, and you might wonder what this has to do with the previous courses we had on unsupervised learning and matrix factorization, but it does have a lot to do with that. So let's see. So the motivation is that we really want to find features to represent text. So, and what that means is that in the maybe most fundamental examples, you have given a word. So there is a fixed vocabulary for, let's say there exists like 10,000 words or so. And you want to map them to features. So WI, if it's in bold, that means it's a feature vector. So one naive way to do this is how would you choose your dimension, right? So that you can represent all the words. So so here you want to map from a word to a feature vector. And then it's the dimension. Now the point is that the word is actually it's a discrete thing, right? There's only 10,000 of them, so we go from a discrete object to a continuous object, so continuous representation. So that's kind of the key aspect, right? We want to learn continuous representations, and how do we do that? So does it even work to represent such discrete objects in a continuous space? So continuous just means this is real numbers, right? It can be any arbitrary number, higher or lower, also fractional numbers. So the easiest way to do that is to just take your word and map it to which kind of vector. So the easiest way is to just map it to 0, 1 vector, which has zeros everywhere, except 1 at a very particular position. And the position of that 1 is as position I, where this is the number of my word. So there you put a 1, and all the other things you just put to 0. So that is called the one-hot representation. Position I for word I, so that means like it's a one-hot vector. And the other name for this is that this representation here is called the bag of words representation. So this is bag of words. Why is it called that? It's called that because you can also do it for entire sentences. So if you have more than one word, then you can just put ones at all the positions where you have a word in a sentence, and then it's called bag of words because this completely ignores the order of the words, right? The ordering of the sequence. So it will just mark all the words which are present, they have a 1, and the others are not. So that's why it's called a bag of words. And this is a very standard and very also successful, actually, feature representation you can use for text. So, for example, on top of these features, you can put classifiers, you can get excellent text classifiers and so on. They're not always perfect because they're not robust to slight changes in the word. For example, if your word has a typo, then that has nothing to do. So its representation you get will have nothing to do with the representation you have for the related word, which has no typo, but should mean the same thing. So the dimension, so here is maybe the vocabulary size. So it's very high dimensional, which can also be a problem, for example, in terms of memory. So these are some downsides of this representation. Question now is, can we also find other representations which are maybe a bit less high dimensional than the vocabulary size? So can you find like a 10-dimensional space which represents all the words nicely and also respects that their meaning, right? So here is a space which you would like to have. This is of course just an ideal picture. You have 3 or 10 dimensions, and you hope that the related objects are close together in this space. Related words should be represented by vectors which are close in this space, and objects which are not related, they should be far from each other. And that's really the key concept which we would like to have, what it means to get a good representation, that it kind of reflects the underlying meaning of these words, or it reflects the semantics of all the words we have, and also maybe longer texts ideally. So this is the goal, and the bag of words thing is not really achieving that goal yet, because, as we said, it's not robust to typos. But there are other methods, and now you can maybe already smell a bit that maybe this is going to relate to dimensionality reduction, because in all the previous hours we were able to find like 10-dimensional feature representations for all kinds of data. Can we do a similar thing for text? And yes, this is possible. So which matrix should we actually take to then factorize it to get our 10-dimensional continuous representation? So interestingly, this is the exact same thing we have already done for the recommender system. So what we're going to do here is that we will just represent our data matrix as being the co-occurrence matrix of words in all existing text. So what that matrix is just, you just go through Wikipedia and all the news articles in the world, and you count how many times does each word appear together, so just maybe next to the other word. So this one here, what does that mean? It means that the word I appears together with word J this many times in your corpus. It just appears together once. So you just put these counts. And again, this matrix will be extremely sparse, so yeah, you can put as many 9s as you want. So most of this matrix is 0, especially if you have a very large vocabulary. Like if you do this on the internet, there will be a huge variety of words. It's also a very big matrix, by the way, so there can be 10,000 to easily millions of words, which is then one side of this matrix. So the matrix itself is huge. You will not be able to store it as a dense matrix, no way. You will maybe be able to store it as a sparse matrix. Why is that? Because then it's actually just as big as the text you read, because whenever two words appear together, there is an entry in this matrix. So that's something you can store as a sparse matrix. And yeah, that's what you do. It looks like the Netflix price, but it's just that the data has come from a different source. And I mean, even if the mathematical technique is the same, which you're going to apply now, the genius of this application here is kind of to identify how to represent our data and how to turn it from data which is just there. So this is why it's an unsupervised technique. It just uses text which is already there. How to use that signal to produce a representation for words. So how is this going to work? Exactly same way as in the Netflix price in the recommender system case. We will just factorize this matrix by narrow matrix W and a narrow matrix Z. And again, we will just gonna use a small dimension K, which is the number of features that we generate or we learn from this. So, and again, what's the point? The point of this is that if I take now the representation of my word I, so that's the I's row of the W matrix, and multiply it with the J's row Z, and then what do I get? Then I hopefully get exactly this entry here, which is the count of how many times have word I and word J come together, appear together. And the other entries here, I just don't care. I have no information there. You could also treat them as 0. That's another possible method, but it's actually much better to treat them as unobserved and only work with the observed entries. We're gonna discuss this a little bit more in a second. Okay, but I hope the idea is clear to learn these two matrices here. So then for each word I, you learn a representation. Actually, you don't need both matrices. You can just throw away one of them at the end and go extract your word vectors. So each row of this is a representation of a word. So that's what we call it, a word vector. And you can just take these from one of the two matrices and throw away the other. Okay. One small point is that what does it mean to appear together? So you can appear together in a small window. So usually we would say if they just appear together just next to each other, then that's a count. So you can of course relax that a bit, and in practice a good idea is to, for example, 5 words apart. If the words are this close, they appear in real text very closely together. That's an example of how you can define it means to be in the same context. And of course you have to define your vocabulary, which is then determines the size of this matrix, right? So, and here we call this like capital D. We say we have this many words. So you can also, the context, the words you care about and their context words, you could define them differently, but it's usually just the same. So, but you can use a different vocabulary for the context, the columns, than you use for the rows if you want to, but there's no need to do this really. So what I'm saying is, in practice you would just have that this is a square matrix. So that means D equal to N, but you could play around with this if you want. Okay, so that's how we find word vectors, and again how we define our big data matrix X. Now, how is it going to work? We haven't defined the loss function yet, so but you can already imagine that we're going to use basically the same loss function as we had in the recommender system. Just now the data I think is actually much nicer, more natural, and now this is really what you can call an unsupervised learning application, or some people also call this self-supervised, because the system kind of learns to train itself by looking at what is next to the current word. So by learning these patterns which are already there, using them as your kind of labels, that's why this is also called maybe self-supervised learning sometimes. And the learning is to find this W matrix and the Z matrix if you want. So how do we do that? We need a loss function to do that. So, I mean, this we already explained how we're going to factorize it. And then the loss function is really standard. So it's just written here actually. If you look at this, then you again have this set omega, which is the set of the non-zero counts, right? The words which have really appeared together. So if D and N have appeared together, then that means that their count here is non-zero. So that's this count here. So how many times have the words appeared together? Co-occurrence of the word D with the word N. So that's the count you put here. But then, to be completely honest with you, we don't do just that. We actually take the logarithm of this thing. This is just a trick, so it's not, can't say this is a right or wrong way, but that's the idea, to define the data entries. So remember, in the Netflix case we just had star ratings, which were for 1 to 5. Now we have these counts, but it turns out that the most important signal of how many counts you have is better reflected by the logarithm of that count. It's just something maybe a bit more natural, because you don't want to have like 10,000 times more influence just because your word appeared, I don't know, 10,000 times instead of once. So it's better to have the logarithm there, then you can, because it's still meaningful if the word appears together once or it appears 10 times together. So that's why we use this kind of feature transform before we define the data matrix X. And then we use standard squared loss, so compared to the matrix factorization, of course. So that's the same as in Netflix. And then what's also a little bit different is this here. So we have a little weighting factor which depends a bit on the importance of this particular position. So that's something we did not have in the recommender system. And that's just a trick to customize this a bit more, and this way people got a better accuracy from this system. So I'll tell you on the next slide on how this weighting works. But just to take a step back, so what are we actually doing here? We are learning these word vectors, which are the rows of the W matrix. And so these are word vectors. You might have heard of these word vectors. So there's just two standard examples. One is word2vec, and what we're doing here is a variant of that, which is actually called glove. So, which means something like global vector embeddings, and this is the variant that we are explaining here. So if you find your word vectors W by solving this minimization here, then that is what glove is. This is a very, very nice method, and you have already everything you need, right? Last lecture we explained how to optimize loss functions like this with stochastic gradient descent. We just have to build this co-occurrence matrix on counting. So we just stream through our text and build this matrix of who has appeared together with whom and how many times. This is actually a very nice task for MapReduce, if you're familiar with that. Build this matrix here and then factorize it. So that's how this works. And so yeah, this is the whole method. The only thing I didn't tell you yet is how to choose these little weight functions, the f's here in front of the squared loss. It's not so important conceptually, but in practice it does influence the performance quite a bit. And by the way, glove has been invented only 2014, so now we're getting into quite recent methods in representation learning. And since then, I mean, it has been quite amazing that the whole natural language processing has been transformed completely. Like, I mean, before 2013, everyone was using this simpler bag of words representation, right, like this. And then when this method came up here, which we are now discussing, and also word2vec, which is basically a very similar thing, then every NLP application since then has been kind of transformed by that and has been replaced by using these as features instead. So whatever system people build, what they do first is to do this, to take the words, transform them into word vectors, and then take it from there. So this seems to be a very elegant way to go from discrete data, which are words, to something continuous, right? So that's why we have done this factorization here. So we've done like a dimensionality reduction. Now we have continuous features, which is really what deep learning methods like and excel on. So after you have this, you can plug this into any machine learning model you like, also deep nets, of course. Okay, so what are these weights? And again, I don't want to make a huge story about it, but people choose it in a particular way that it depends a bit. So here is your observed count. How many times have the two words D and N been appearing together? So that's your kind of input, and we make the weighting dependent on that. So, and what we do also here is this is some kind of a cutoff. So this you can see here. So whenever the count you have is bigger than that, then you don't care anymore, because then the answer will just be 1. The weight will be 1. It will just count as usual. So on the plot here you see on the x the count, and on the y you see the importance weight. So and so why is that happening here? So again, this is a smart weighting to decide. In the recommender system, it was just kind of binary. The words which are not here we don't count, and the ones which are here, they contribute 1 unit to the loss, because all these stars were counting like equally. And now we have a similar thing, right? If you counted 0, then you count 0 to this loss function. That's the same as saying that you are not part of the loss function, you're not part of the omega set. And then if the count is very small, then it means we have a kind of a smaller weight. So those pairs which appear rarely together, they count a bit less to our loss function. And then the ones which are quite frequent, they do count fully, which means that their count is fully taken into this squared loss. So that's just kind of a weighting which improves performance empirically a little bit. There's no theory for this, so I should maybe brand this as a heuristic. So and just kind of a trick to make this weighting a bit practically better. So. And they also put a special growth rate, so they don't have really a linear growth from 0 to 1, but the growth is a bit curved. So, and that comes from this alpha exponent which they have, which is chosen somehow like this, because they did a cross-validation and found this to work best. Another cross-validation you have to do, which is actually a bit more interesting, is of course the question we always get, how to choose k. Because this is really important. This has a huge impact on any application. So because this answers is how many features do we have. So whatever you want to use your word vectors for, you need to maybe respect the capacity or what input this later machine learning model wants to expect. So maybe it wants to have 100-dimensional word vectors. Maybe it wants to have smaller ones. Because to store your word vectors, to store your W matrix, that takes a lot of memory, right? So it's a K matrix times the size of the vocabulary. So this is easily 1 million. And the K maybe is 100 or so. So also in modern NLP applications, this is up to 700, 1,000, the dimension of these vectors. So this W matrix can be quite big. It can go into the gigabytes easily. So that is also going to influence your decision on how big you want to choose this K. Okay, and if you have freedom how to choose it, then you can do cross-validation to see what performs best for your task at hand. So this is GloVe, and again, very impactful paper from 2014. But one has to be honest, this was not exactly the first version of word vectors, because the first one was just a year before that and was called word2vec, which we also gonna discuss in a little bit. And before I mention that, I also want to mention that, yes, you could even be more naive. You could even say that I don't want to deal with this weighting. I don't want to deal with the missing entries, the omega. I don't want any of this. I will just treat my matrix here as a full matrix with zeros at the unobserved positions. So that you can also do, and then you can do the SVD, the singular value decomposition. It's also a way to get word vectors. That would be the even easier way, which just means I take word co-occurrence and basically then I do PCA. That's another alternative. It turns out to not work so well empirically, but it's still a nice method. And what is also interesting is to say that what we have here is to ignore the unobserved entries has actually a huge computational benefit. Because stochastic gradient descent, as we have seen, it will only care about the observed entries, and it can learn the W and Z already from that, and very efficiently. One step of stochastic gradient descent costs only the order of K, which is much cheaper than if you need to deal with a dense matrix or anything. So this is orders of magnitude faster to train. Maybe that's another contribution, that this has found much more success than just doing the SVD of this sparse matrix. So okay, and so that's GloF. And what is this useful for? Yeah, so far you were just maybe not believing me or believing me if this can be used for further machine learning applications afterwards. So the beauty of this is that this is trained unsupervised, and then you can just use it for any purpose you want. And if, okay, the thing itself, these vectors themselves, they also show some interesting patterns. You have probably heard about this, that the usual stuff. So if you take the vector from man to woman, so that's you can compute this difference, right? That's a vector in space. So you have trained your word vectors, and now you just look at 2 points, man and woman. You look at the difference vector, you take that difference vector, apply it to king, and you get somewhere in space. And the point you get to is very close to the word queen. So that's nice. So I mean, you don't get exactly to the point which represents queen, but you get to a point in space where the closest word is queen. So that's the idea of these word analogies, for example. And this also works for like kind of verbs, times. So for example, you have an activity in the present and in the past. So you can take this vector from present to past, attach it to another word, get somewhere, and see the closest word there is the past tense of that other word. So that means that this space reflects quite a few of the interesting meanings that words can have. It also works super easily for like countries and capitals. So if you have one relation from a county to its capital, you can attach it to another country, and the point you will get to there, the analogous point there, will be very close to the capital of that county. In most cases, it's not perfect. You can see it's a little bit tilted, but what's kind of beautiful here is that this system knows nothing about the true logical meaning or the context of this, or what this actually has to do with the real world. But this is purely unsupervised, only based on the counts of how words have appeared together in all the text in the world. Just because from that you can do this matrix factorization, and you get some very, very beautiful patterns, which are also useful, because that means that it understands a bit the meaning. So it also understands synonyms. So synonyms are words of the same meaning. They're represented very closely in that space. So, and yeah, people have tried all kinds of tricks. So if you take a hockey team belonging to a city, you can take that vector between them, you can attach it to another city, and then you also get usually the right thing. Doesn't always work, and yeah, it's getting funny when you do it with people. So you can ask, who is the Steve Ballmer of Google, or things like that. So it gets quite interesting sometimes. There's some demos online. I encourage you to play around. And yeah, you can also download this and play in the projects. For example, there is also the project we have on text classification, if you want to do that. But even if you don't do that, you could also still play with it, because we do provide actually code for the GloF word embeddings. It's already available now on the GitHub. Okay, how does it work? How do we train it? We've asked this question a few times in the course, and the answer was always the same. It's also still going to be the same here. That's the usual stochastic gradient descent. And again, so I would encourage you to look at the lab, and the efficiency of this is really key. The efficiency per iteration is is order of k, which is independent of the number of words we have. So it's independent of this gigantic size of this matrix. So it's quite fast. That's very nice, and this also makes this a successful method in practice. And yeah, it's mathematically identical to what we have done for the recommender system. It's just a very, very different application, and has taken a long time until people realized that the same thing can be applied to these very different applications. Okay, yeah, you can modify it a bit, you can do regularization, you can ask how we can parallelize this, so there's still a few open research questions there. There is one major downside of this, of GloVe, so, and that is that we have to pre-compute this entire matrix. So the matrix itself, the co-occurrence matrix, is very big, so is to just pre-compute our input matrix. So pre-compute this X, and this is a gigantic work, and then also this makes it kind of hard to hold this X matrix in memory if you are on a moderately sized computer. So that is a downside, and also it's, yeah, you cannot really just stream through the text and directly train your word vector, right? You can stream through your text to build the X, but then that's the first stage, and then in the second stage you take your X and have to have it in memory and do this vectorization. So that's a big downside, and that's why GloVe has actually been a bit less popular than this other method, which you might have heard already, which is called Word2Vec, and that is actually from 2013, and has already found a huge impact, and 10,000s of citations, and even more importantly, also a lot of usage in any industry use cases as well. So this is very, very widely used, and kind of, yeah, because it's also kind of a simple method without too many hyperparameters, which is just working quite nicely. And the key part that I wanted to take away from Word2Vec is that it can really do this streaming, so it can solve this main downside of GloVe, which you just have mentioned. So that's why we like Word2Vec as well. So what this means is that you just stream through the text. You get so that's like, for example, Wikipedia or all the books which are available online, or a crawl from the web. So you have sequences of words, and then at some point you have word WD, and then you have word WN, they appear together. So is it possible to train this on the fly, to just stream through the text? So that's the question, and Word2Vec is actually doing that. So how is this possible without us ever building any matrix? And can we still train our word vectors right while reading the text in one stage? So that's the streaming algorithm, and that's what I like to study now. So the conceptual idea here is to just separate real word pairs from fake word pairs. So word pair means that D and N, they have appeared together, right? So that's a real pair. And I want to now build a system which can say that yes, this is real, versus if you give it another pair. So here's a word which appears like 10,000 words later. So I don't know how I want to call this Q. So this is kind of a negative. No, I call it N prime. So that's a word which appears far away from the current D, And that's what we call a negative example. So that one is something I want to not count as a pair. So WD and WN together, they are not a real pair. So they are a fake word pair. And these two guys, they are a real word pair because they do appear together. Okay, so it sounds like a classifier, right? Fake against real. But the classifier needs to take two words and then make the decision. So what's the simplest way to do that? I would argue the simplest way is actually to take the current word vector we have of our main word D and to multiply that with the one of our neighboring words. So that's the real pair, WN. And then I want to do the same thing with a fake word. So that's the one which has not appeared nearby, but it's further away. That's N prime. And I want this guy to say no, and I want the real guy to say yes. So that's the idea. So the classifier is super simple. The classifier is kind of just defined by the yellow vector, and the way it works is that it has to say yes, and he has to say no for the other one. So that's the no would be a negative score. And the yes is a positive score. Okay, so this is what we're trying to do. And what we did is we just took the easiest classifier you can get by just using the word vector itself as the classifier vector. So that's very interesting because there's no other model here, right? We can just say every word is its own classifier, and the job it has to do is to say if other words which appear together with it are actually real neighbors or not. So, and the way we do this is just we train the system with stochastic gradient descent for this value to be high and for this value to be low. So, and we can do that while streaming through the text, right? We always are somewhere, so we always have a yellow and a green word which are just right where we are. So that's a real pair. That's one we will use to update our word vectors with gradient descent to make this big. And that everywhere we are, we also take some fake words, which you just take as random words from anywhere. These are called the negative examples. So you pick one of them or a few of them, and then you change that this value should be low. So you do also a gradient update for your vector such that this is low. And that's word2vec. And the usage of these red guys, the negative example, is called that's called negative sampling. And so this whole principle is also quite fascinating. So what's happening here is with this real versus fake, that's called contrastive learning. So and that's a very important paradigm which now is getting a lot of traction, not only in text, but in all representation learning techniques. So we also see that for images, people have now found state-of-the-art techniques which use this paradigm, to find better representations of like regions of pixels, for example, in images, or also any other data domain you can imagine. And the point here is just that what has happened is that we have kind of used additional signal, right? We don't have many manual labels for stuff. So here there's zero manual labels anyway. But what we do have is we have a lot of these co-occurrences, right? That we have words which appear together in the real data. And then we have as many as we want of these negative examples. So we do have so many examples. So we will just use that signal to say that the representations of the actual true guys together have to be close, or here have a big inner product, and the ones who are far, they should have a representation which is far from each other. That's the idea of contrastive learning, and here this is just used by the inner product. So that's how we measure the score in this simple model. This is the very simplest way to define a classifier which we can classify any pair of things. You just give a vector to each thing, and then say that the ones who are close should say yes, and the ones who are far should say no. So this is word2vec, and yeah, contrastive learning is a cool research area which is getting a lot of traction at the moment. And the beauty of this as well is that it's so efficient to train. So we use 3 and 3 text. You just update 2 vectors which cost you k, and one of these, and then you continue to the next pair of words. So word2vec, and I hope this was more or less clear. So it's kind of a fake versus real classifier. All right. Yes, I would also recommend to implement this and play around, especially if you're interested in text. And again, this idea is useful for other data modalities as well. So whenever you have things appearing together, so people even use this in many other applications. For example, you can do this for industry applications like ad placement, or if you have users and products, people visiting your website, you can also use similar ideas here. That if people have clicked on that item before, you can use that click signal to actually train vectors like this, because then the product and you as a user have appeared together. Therefore, you can use this signal to update the representation, the vector of each user and each product. Or also you can do this for websites or anything you want. So this is also a kind of an important trend in research these days, to just kind of try to find embeddings of anything. Just try to find a meaningful embedding of the thing, ideally even in a space where it's compatible. So here the words and their context, the thing they appear with, they are embedded in the same space, so we can actually very meaningfully compare these with each other. And that basically is still the same matrix factorization idea, so as we've already been discussing last time. Okay, word2vec, and then now for something completely different. Well, it still is closely connected, is to look at another way of unsupervised training. Well, very closely related to what we just discussed. So, and that's just, I'm given a sequence of text. So word 1, word 2, word 3, and word n, and then I'm just asking, how do you continue this? So can you find the next word? Can you find a continuation of text? And again, you can do this on the whole Wikipedia. You just start with something, and then you always try to predict the next word, and you continue. So a system which can do that is called a language model. So it's just like a next word predictor, and then when you achieve to do that, what you have is actually, now you have trained a model which can generate text. So because it can generate the next word. So once you've trained such a system, it's quite nice, and that also we have seen a huge progress in recent years and so on. So you might have heard of these gigantic language models, GPT-2, which was last year, and GPT-3 was this year, which is a model which has 11 billion parameters. That's quite a lot, because there are not so many words, right? The words are, maybe you use 100,000 words usually when you work with text, for example, in English, or even less. But this model has so many parameters. It's a deep net. It's actually a transformer model, which means it's an attention mechanism. which is quite a simple neural network actually. It's very close to the standard feed-forward fully connected layers that you already know. It's a slight modification of that, but it's something which is less complex than convolutions. So this is just a very simple network, but quite big. And the main interesting thing about it is basically how it's trained, right? How do you even manage to find so much signal, so much useful patterns, or so much labels to train a network that big? And the task it's trained on is exactly this one. So it's just trained to always continue text. Take the text from Wikipedia and start with a few of the words, and then always continue predicting it, and you get a loss function if you predict the next word correctly or not. And for example, you can just use a multi-class classifier of the vocabulary size to say what is going to be the next word, given that the previous few words I have seen, maybe the 3 previous ones are these. So that's what I know currently. Given these previous words, what is the next one? And that's just a multi-class classifier. So that's exactly what these gigantic language models are doing. And because you have so much text, this fake training task, which is kind of a self-supervised training task, this task manages to train these models in a meaningful way. So you can call this either self-supervised or unsupervised, again, because it's kind of defining to train itself on the next word, and that's what it's all about, right? It's not about what is the neural network architecture or how many parameters it has, right? The key aspect is how it's trained. That people have identified that this is a way to train a model. This is a task where it can train itself. And then you can plug in any network you want. These networks a year ago and this year, they're actually the same. It's just that this year they managed to train even a bigger one, but there's no change in the algorithm and also no change in anything with the model otherwise, except that it's a bit larger, and also no change in the task. The task is always this one, the training task. So you should definitely play around with this, because these are the best text generating models in the world currently. I mean, any model trained on this, that's what I mean. There are many variants from academia and different companies who produce their language models in this way. And then once it's trained on this task, it's used for another task, right? It's just because it can do the task, it means it learns something useful. That means you can again use the representations this it learns. So you can use these feature vectors this model has, take them out, and then use them for any other machine learning task. So this is nice. And yeah, there are like two variants. Either you predict the next word with a multi-class fashion, or you just do the real versus fake. Then it's very similar as in word2vec. But actually the first one is more common at the moment. So it gives a bit more signal to really use exactly that it's this word. You get a lot of information. You want to use as much information as you have present in that text. Use that information to update the weights of your model. And maybe we can have a short look at how to write with these things. So what should I say? A machine learning exam. Why do we have to? So I can write any few words, and then I will just trigger autocomplete to continue to continue this text. So and then you can see it will just always suggest some stuff. So it doesn't necessarily make sense because I didn't give it any information, right? This is just naively continuing the sequence in the way it thinks it's most probable. So given that what it's been trained on. This is the same thing as you do auto regression on on a time series. I mean, you're just trying to continue the time series, and your model has been trained to do well based on the past history. And here the past history is just all the text in Wikipedia or some other data. So this is not the newest language model we have. This is, I think, GPT-2, which is kind of already 1 year old. But this, what I'm trying to get across as a point is that it's very realistic. It can produce text which looks like written by human, and that is actually opening a lot of interesting applications. So this is also having some nice applications. For example, if you start, even you can start writing source code. You can write some HTML code here and then let it continue that. And so it's quite broad. And what the hell is this text? This is really funny. So I need to continue this text maybe. So okay. I don't know why I did a white space. So anyway, can write text, and this of course also comes with some dangers, that it's becoming harder to distinguish what is written by humans on the internet and what is written by such models. So it's not always so clear. So this can be abused to generate spam, to even interact with people pretending that the system is human. So this is where it can have many problems. So okay, it started to write some kind of business style, blah blah. So yeah, okay, why is this interesting? So it also the best conversational agents that you have, like so chatbots, they actually, the best ones we have are also just that. They're just a simple language model, which is just a big neural network which just tries to continue text. And because this has been trained on a lot of data, so this is also able to do conversation. So this can say, so you just give it some context. So you say person A says this, so student A says says this, and then you give another line. So for another person saying something, and then you try to continue the conversation. So I think it's okay. Let's see. So if you can also mimic conversations, so it can actually. I'm just making a new line here because it doesn't seem to get that. So it was actually continuing correctly. It was saying student A was saying something and student B was something. So now it gets to okay, now student A is talking again. What's gonna happen next? It's a bit slow. Ah yeah, there's a colon. And does anyone know how I can get rid of this keyword? And so it can really mimic conversations, right? So you can imagine you have a conversation with this thing where the student A is real, and then whenever the system is asked to have their point in a conversation, then you just give the conversation so far as a text, and then the language model continues. So okay, I'm slow here, but it's working pretty well. Maybe this is not the best example because there's nothing optimized here. I was really just going with the default parameters and putting a random text. So this is not something I've cherry picked. You can play with this as well on your own. So this can have conversations, so then it can also be used as a conversational agent on the web. And now I think it's done with a sentence, and now it will maybe switch to student B again. So yes, so it's mimicking a whole conversation. So, and that of course can also have many dangers, because then this might also have issues again with real versus fake, or if it's gonna lead to bots on the web which generate fake context, which try to influence people on Facebook, for example. That's something that could happen with such systems. And they are also interesting because it's so resource intensive to train such models. I already gave you the whole algorithm. The algorithm is just stochastic gradient descent on a lot of text. But what's kind of interesting is also that it takes so much energy to train such big models. So some of these recent models, they took hundreds of thousands of dollars or francs in electricity cost alone to just run this training. And then it's also can be an issue of who actually does have enough resources. If you're at the university, do you have, or in a small startup, do you have enough resources to train a good language model? I don't know for what purposes you want to use it, but so this, I don't know if that's an issue, but something that should be discussed as well. That this is something where if you throw more electricity at it, more money, then it's also more environmental impact. That's something that you can discuss. But also it's something where it's quite clear that the more resources you throw at it, the more accurate you can build such a language model, which might be useful for a very large variety of applications. Some very useful and with a lot of benefits, and some might also be a bit concerning. So that's something really interesting to discuss. And I think that's an interesting thing, because it's kind of so simple, but still it needs a lot of compute to make it work well. Right, the idea of language models is of course many decades old, right? The way to train something like this, it's the same as doing autoregression on the time series, as I said. That's of course not new. What's new is that it actually works empirically on text, that we now have neural network models which are big enough and can be trained. We have enough compute to actually make this work and to generate very realistic text. So, and not only generate text, but also then use this model to give features. So now you can have sentences, and the status of the neural network, for example, in the last layer, that's a great representation for your sentence. So that's how you get how do we get good features from that? So it has kind of two purposes. So to get features. So that's the representation learning part, and the other part is to actually generate text. So there's two applications you can do. So these are language models, and yeah, very interesting developments as well. So yeah, I think we have already seen two very cool applications from text. There is another one which is kind of close to this, is to use a bit more traditional supervised learning, or use more traditional neural networks like convolutional nets can of course also be used on text. I mean, maybe I shouldn't say of course, because it's not super obvious, but let's say, let's ask the question, can we use a convolutional network to take a sentence, wait for the video and don't rent it? So we have kind of a sequence here. And so I want to take this sequence of text, and can I get a representation of this entire sentence, right? Because so far we only talked about representations of words. So it might be interesting to ask what can be done for whole sentences. Well, the language model I explained before is also for whole sentences. That's another way to deal with it. So, but let's say if you want to use a convolutional network, then that's also something you can do. And what you will do is that you start from the word vectors. So for the word weight, you have filled this word vector into your row. So for example, you have 100-dimensional word vectors. You just fill them in the rows of this matrix, and then you have this kind of matrix of variable size. So that's a key aspect, that not all the sentences have the equal length, right? That's why it makes it a bit difficult to apply traditional neural networks on text, because on a short sentence and a long sentence, the input would look very different. So, I mean, the K is always the same, but the length of the sentence varies. How can we deal with that? Another easy way to deal with that is this one here, that you actually use convolutions to deal with that. And it's very simple. It's just to use a convolutional filter which slides over the text. So this is this kind of filter which takes a matrix which is 3 by 100. It takes all these entries, this is this window of the convolutional filter, takes them, multiplies them each by weight, and outputs one number. And that number is going to be the result in this red box here. Now it's green. And that's what a convolutional filter is. You remember this from the course you had on CNNs a few weeks ago. So what it actually does here, if you think about it, is just treats the whole big matrix here as an image, so to say. And then he has these convolutions which are just sliding over the input. So the same filter then is applied like further down, like here, right? And then on the very bottommost part. So that's what the convolutional filter will do. You would just compute one number for every position in your sentence, and then you have found a representation of your sentence. The problem is it's still variable length, so we want to kind of find a fixed length representation of our sentence. So what we do is we take the max. So now we still have all these entries here, right? There are too many. So I take the maximum over all these entries. That's max pooling. You can take the average if you want. That's called average pooling. But maybe the maximum is a bit nicer, because it just means that it has like one thing it should pay attention for, and it tries to find that, and then you can say that thing is taking care of that, and if it's there or not, that's your feature. So now you have a fixed length representation. So which is very nice. And then finally you have some kind of classifier which is supervised. So here on the last layer you just have two neurons, so that means it's like a binary classifier. So for example, if you use sentiment detection, then you can try to build a classifier which can say if this whole text is positive or negative. So that is a supervised signal. For example, these are manually annotated, or you can also use maybe smileys which are present in the text, which is again going a bit to this idea of, can we build a signal ourselves, kind of a fake training task where we can learn something, and seeing if your original text had a smiley or not is one such possible signal. But you can also use any manual signal if you want. If people have annotated your text as being positive or negative, like experts have annotated that, that's of course also perfect. But manual labels are very expensive to obtain, so we'd really prefer to have more labels, but obtain them in another way. So in a semi-supervised or self-supervised way, for example. Okay, but takeaway from this slide is basically just, can you use standard convolutional networks on text? Can you use them to get sentence representation? And the answer is yes. So this has also been successfully applied, for example, to tweets and sentiment classification many times. Okay, but nowadays, instead of these CNNs, people rather use these transformer models, which seem to work even better, slightly better. But again, the key aspect is not so much the model in my view, but the key aspect is how it's trained. What is the signal it's trained on, the training task. Okay, so that's kind of a summary. And so yeah, there are a few more things you can do. I won't go into detail here. So there's combinations of what we have discussed to how to take word vectors and build sentence vectors. The easiest way is just to average them. Another way is to train them such that they can be averaged. That's another thing we actually worked on. You use the same thing as like glove vectors or word-to-vec vectors, but here you specifically train them such that they can just be added over the sentence, and that the resulting vector from the adding is good. Of course, you can always add them, but the question is if it's good or not. But if you actually always add them over the whole sentence, even during training, so that's kind of the position where that would happen is kind of here, right? How you go from variable length, which is just a sequence of word vectors. Forget about the convolutions. If you just want to go directly from the word vectors to a sentence representation, then either you can just average them, or you can average them such that you train them such that they can be averaged. And yes, nothing, I'm not going into detail here. What I want to mention is that one also very nice NLP library, which is for like supervised. Sentence classification, so you can take sequences. You can take a sequence of words of variable length, so that's a sentence, or short text or paragraph, it doesn't matter. And you can do classification on top of that. And why I mentioned this one is that it's also a very popular NLP library, natural language processing. So a good software package which is extremely fast. And why is it so fast? Again, the reason is exactly what we discussed in this hour. Because it's a matrix factorization which is trained by stochastic gradient descent. But what we have seen so far was completely unsupervised when I showed you the word vectors, right? But what we see here is a supervised training scheme. Actually, FastText has two training schemes. One is supervised, one is unsupervised. But here I want to focus on the supervised for a second. And tell you how that works. So mathematically, what function is it optimizing? Why is it a matrix factorization? And the way it works is also very, very simple. And so for the notation, we introduce some x vector, which is a bit strange, but that's just the bag of words representation of my sentence, and that is, let me visualize this here. So bag of words, you remember this was from the very beginning. If you just have one word, we have only one entry which is non-zero in our vector. But now if I do this for an entire sentence, then we maybe have several non-zero entries. So here we have a sentence with 3 words. So in these positions here it has ones, and everywhere else it has zeros. So that is this x vector. And then what happens is that it gets multiplied with a z matrix. And that is very simple. So Z transpose, and what happens if you do that is pretty clear. It will select the columns of the words which are present in your sentence. So this Z matrix it contains the word vectors actually. So again, it has k rows, and that's what it's doing. It's like storing the word vectors as we had before. It's just maybe it looks a bit different than you saw it last time. So this is the Z transpose matrix. So what's happening here? So nothing special, just assume that these vectors are already there, stored in the Z matrix. We have one column per word. And then what happens is that so now you have a sentence which contains a number of words, just 3 of them. What happens is that 3 column vectors corresponding to these words get selected. So the Z matrix has whatever size of V is the vocabulary size. So that's the middle part, and now we are almost done. So what we didn't explain yet is the W matrix. I'll explain that in a second. So Z, we're good. That's the Z transpose. And now there is another matrix here, W. And to be honest, it's actually not really a matrix. So the W is only one row. So that's a bit boring. So here's your W. You just multiply this by one row. So W, what it is it's just a classifier matrix. So that is what's happening here. And what's happening is that, so you from Z times X, you get your sentence representation, and then you multiply with the classifier W. So and the sentence representation is just obtained easily by adding those word vectors which are present in my sentence. Okay, so Z transpose times X, that is my sentence representation, and XN is my current sentence. And then I take my sentence representation and multiply it with this yellow vector. And what does that give me? That should give me again a classifier, so it should be a high score if the classifier is what it is. So the labels Y's are actually plus minus 1, so you want this to be high if it's the positive class and low otherwise. So that's so the Y's are the labels, and it's just that, okay, if you want this sentence to be positive, for example, positive emotion. So again, this is supervised learning. So every sentence is labeled with the label YN. So if this one is plus 1, then you want the whole thing to be positive, and then F is a function, well, you can ignore the F, it's just going to be a trying, so then it's correct, right? So you will have nothing to pay. But if the label is wrong, it's negative, then you also want this to be negative, so you want the F to actually reward you to give high values. So it's just a classifier. So the whole thing here is just a logistic regression. Basically, you can, well, it's the same thing. It's a binary linear classifier. So yes, no, right? It's a two-class problem where the labels are given by annotators, and so it's just a classifier, the W itself. The only thing which is special here is that W and Z are kind of learned together, right? The learning here is happening again for both, right? The word vector Z are learned, and also the W is learned. So W and also Z, they are learned at the same time. So that's why it's a matrix factorization, because the loss we have depends only on the product of the two guys, which we learn, and that's therefore it's a matrix factorization. Just here we have used a supervised signal, these given labels. We have used that to train a matrix factorization. And interestingly, this very simple classifier performs way better than a simple linear classifier on the raw features. If you can already directly use this as your raw feature and build a linear classifier just on that. So that would mean I directly learn a W matrix on top of this of size words. That works very poorly. Even if the W you need here for direct classifier would be very big. So this does not perform well. But here we first have learned sets which go to a k-dimensional space, which is actually lower. So k is like 100 or so. So I go down from 1,000,000 words to 100k. And then I go to this W, which is a classifier vector, which is only size 100, so quite small. But the answer from that is way better because it learns the W and Z to go well together and together learn a non-linear relationship. So you know this, right? Because it's a product of two variables, so it's something non-convex, also clearly non-linear. And therefore this is a little bit a more powerful model to learn that. It's a bit like having one hidden layer in a neural network, so having like two effective layers. So it's something a bit more powerful as a model. And why this is so efficient is again for the same reason as we have seen with stochastic gradient descent. Because if you train this with SGD, you just feed it one sentence. You feed it as this sentence which has only a sparse set of words which appear in it, so only very few of the columns will be needed, and only the ones which are actually needed here, only those will update their weights because only those will influence the loss function. So again, basically the complexity to do one stochastic gradient step to optimize this is order of k, which is very small. To be honest, it's order of k times the sentence length, right? Here I have sentence length 3 and k maybe be 100. So in that time I can update the relevant columns of Z and also update the W, which is of course super cheap. It just costs me k. So SGD again with very good efficiency. This algorithm is hard to make fast on a GPU, but even on modern CPUs, on multi-core, this runs extremely fast and is much faster than most other even GPU-based text classification models. So very, very nice way to do supervised text classification. Okay, so I guess that is it for today. We have seen a few fun applications in unsupervised and supervised matrix vectorizations for text, and also seen a few of the impacts on text applications. If you want a few more pointers here, some links, and yeah, play around with these demos with the transformer models. Very cool topic at the moment. So I think that was it from the official content of this year. It was a pleasure with you. I hope it was okay despite Corona. It was very unfortunate that we didn't have enough personal interaction. I hope we can catch up on this on other channels, on the forum, on Discord, and yeah, see you next week. Thanks a lot. So.